Alright, in this video we're going to talk about more partial fractions, and what we're going to do is talk about actually figuring out the coefficients this time. So suppose, again, I've got a a partial fractions problem, and suppose it factors, if it's not already factored in the denominator, as x plus 1, x plus 2. So suppose my original problem could have even said integrate x times x squared plus 3x plus 2. So this would be the problem as it's stated, and then I would basically take the denominator, factor it into my two linear factors. So using what we talked about from the last video, each linear factor gets its own fraction, and then again we put just generic numbers a and b on top, and we're going to have to figure out what a and b are equal to. So in this case, what you do is you basically now get rid of the denominators. I'm going to multiply both sides by x plus 2, x plus 1 in this case. Whatever the denominator of your original problem is, that's what you're going to multiply both sides by. So I'm going to multiply the left side by x plus 1 times x plus 2, and if I do it to the left side, I have to also do it to the right side. Okay, so on the left side, everything's going to cancel, and you'll simply be left with the numerator, just x. On the right side, when you distribute the x plus 1 times x plus 2 to the first term, the x plus 1's will cancel out, leaving you with a times x plus 2. And then when you distribute the x plus 1, x plus 2 to the second term, the x plus 2's will cancel out, leaving you with b times x plus 1. Okay, so at this point, let me show you the trick, and also let me show you the long way, because, well, if the trick always worked, we would use it, but it doesn't. What we're going to do at this point is, basically we have an equation where things are equal. Hey, it's an equation. What we're going to do is we're going to try to make either the first term on the right side disappear or the second term on the right side disappear. And the way we can make them disappear is by picking clever values for x. So notice if I let x equal negative 2, well, you plug it all into your equation. On the left side, I'm simply going to get negative 2. But notice on the right side, I'm going to get a times negative 2 plus 2. And then on the right side, in the second term, I'll get negative 2 plus 1. Well, negative 2 plus 2 is 0. 0 times a is 0. So I've now managed to just get rid of this first term. Then I'll have b times negative 1. And solving this for b, negative 2 divided by negative 1 is going to give us positive 2. So I've now figured out my b value. In the same way, okay, we let x equal negative 2. Now we can pick, well, what would get rid of the b term? How about x equals negative 1? So now the idea is, if you plug in negative 1, again, back into your original equation here that we had, you'll get negative 1 on the left side. On the right side, my negative 1 plus 1 will be 0. The b will disappear. And you'll be left with negative 1 plus 2, which is positive 1. And you'll simply get that a equals negative 1. So this is kind of the little trick to figure out a and b real quickly, in more terms as well. You have to be a little careful, but this trick basically works when you have linear terms. So what it says is this fraction x over x plus 1 times x plus 2, it says I can actually rewrite that as a, which is negative 1 over x plus 1, plus b, which is 2 over x plus 2. I'm just filling in my original thing up at the top with my a values and my b values. So equivalently, if I wanted to integrate this thing on the left, I could now integrate the stuff on the right, And the trick is you're going to do it basically a piece at a time, using natural logarithm functions in this case for linear factors. Okay, so that's the idea. You're trying to take kind of a longer problem and you're going to bust it up into hopefully some easier problems. Okay, and I'm not going to do the integration just yet. Again, we'll talk about that in a second. So let's do the method of what's called equating coefficients to figure out a and b. So again, the idea is the same. You're going to have to use this on quadratics. So I'm basically just trying to give you a heads up on what's going on, just so hopefully the quadratic ones will make a little more sense, the irreducible quadratic ones. So again, we start the same way. We factor the denominator, we write out its partial fraction decomposition, and then we get rid of the denominators. So I'm going to come back to this equation, this x times ax plus 2 plus b times x plus 1. So that's the thing I'm going to work on now. So again, we said we had x equals a times x plus 2 plus b times x plus 1. And now we're going to use this method of equating coefficients. Okay, so equating coefficients, what you're going to do on the right hand side is get rid of your parentheses. So I'll distribute, I'll get ax plus 2a plus bx plus b. And what you do now is you group all of your like terms together. So I've got a couple x terms. So ax plus bx. Again, you still have x just hanging out on the left side. And then I have 2a plus b. So what you can do in this situation, this is what you want to do, you basically group your like terms together, and notice you can factor out an a plus b. You can basically factor an x out, rather, on the first two terms, but I'm going to pull it over to the right-hand side. You could factor the x out front, but again, multiplication, it doesn't matter the order you do it, so you could pull it over to the right side as well. And then I'm just going to stick my constants in one set of parentheses. Well, notice I've got an x term on the left side, but I don't have any constant. That's okay. I'm going to rewrite the left side now as 1x plus 0. Well, 1x plus 0 is certainly the same thing as x. And this is where the equating of the coefficients comes into it. Okay, the coefficient in front of the x on the left side is 1. The coefficient in front of the x on the right side is a plus b. We now equate those things. That means 1 has to equal a plus b. And then we do the same thing with our constant term. I've got 0. Well, my constant term on the right side is this 2a plus b. We set that stuff equal to each other as well. 0 equals 2a plus b. And now you have a system of equations that you have to solve, linear equations, in this case in terms of a and b. So this is why I think it's much easier to use this trick of just plugging in clever values so you don't have to do this. But again, if you have irreducible quadratics, there's just no way to avoid doing this. Well, the easiest way, I guess there's a couple different ways you could do this. You could do substitution, you could do elimination by addition. I'm going to go ahead and do substitution. So if you subtract, you get the first equation, 1 minus a equals b. Probably elimination by addition is easier. I learned substitution first, and I still my preferred method. It's just something I'm more comfortable with. So now I'm going to plug that into the second equation. So it says 0 equals 2a plus b. So 2a plus b, but again, b in this case is 1 minus a. So if I solve this, I'll get 2a minus a, which is a plus 1 equals 0. And I'll get a equals negative 1. And once I have my a value, you can plug it back into either one of your original equations. And certainly if you plug negative 1 in, so we'll plug it into the first one, we'll get 1 equals negative 1 plus b. Well, if you add negative 1, we'll get that 2 equals b. So again, lo and behold, I've got the same values that I had for my a and my b, doing it the way I did it the first time. So again, this little trick is nice, plugging in values. It only works if you have linear terms floating around, but do it as much as you can. It'll still make life a little bit easier, I think. So, but again, the long way, the equating of the coefficients, this will always work. So that's the benefit of it. Longer, but hey, it'll always get you there. Okay, so let's do one more of these using some quadratics as well. So let's do a little mix-up here. So suppose again the thing I had to integrate was, let's make it, who cares, let's make it 3 over x squared plus 4, and let's make it x plus 1 quantity squared. So suppose this is the original thing we were integrating. So again, I have to do my partial fractions decomposition. So in this case, again, I have a quadratic factor. X squared plus 4 can't be factored. And then I have this repeated linear factor, x plus 1 squared. So it says each little thing gets its own fraction. So there's my x squared plus 4 term. And then we have to build up again to this x plus 1 squared term. Alright, so there that is. Again, you take something that's 1 degree less than the numerator on the x squared plus 4 term. So I'll write that as ax plus b. And above the linear terms, you just put numbers. So c and d. So this one's probably going to get a little tedious, but that's how it goes with these problems. Again, partial fractions is pretty long. So sorry this is not all quite fitting in there, but hey, they're just long problems. So I'm going to do the same thing though. I'm going to multiply both sides by the denominator. So I'm going to multiply the left side by this x squared plus 4, x plus 1 squared. Sorry, it's kind of sloppy there. And I have to do the same thing to the right side. So I'm going to multiply by x squared plus 4, x plus 1 quantity squared. Okay, on the right side. Well, on the left side, if you multiply by the denominator, you're just going to get the numerator. So the only thing we're going to be left with on the left side is going to be our 3. And then on the right side, okay, when we multiply the ax plus b over x squared plus 4, when I distribute the x squared plus 4 times x plus 1 quantity squared term, the x squared plus 4 is going to cancel, and I'll be left with ax plus b, and then I'll have the x plus 1 squared terms. And then in the middle term, I'm going to have one of the x plus 1 terms is going to cancel. So I'm going to have c times x squared plus 4, but I'll keep one of the x plus 1 terms. And then when I distribute the x squared plus 4 times x plus 1 squared to the d term, well, d, not b, when the x plus 1 squareds will cancel, leaving me with x squared plus 4. Alright, so yuck, a pretty long problem here. Again, you may want to write this down as we go along at home. It might be a little hard to kind of follow along since it's getting cut off here. I am going to use this trick that we did last time, even though there's quadratics in here. Because notice if you let x equal -1, notice that's going to get rid of this first term, because you'll plug -1 in. Well, -1 plus 1 is going to give you 0. That's going to cancel out the whole first term. It's also going to cancel out the whole second term. Well, there's nowhere to plug an x on the left side, so, well, you're just left with 3 on the left side. Nothing happens. And when I plug -1 in over on the right side, Again, the first term's going to cancel, the second term's going to cancel, and then I'm going to be left with d times negative 1 squared plus 4. Negative 1 squared is 1, plus 4. We'll get 5d equals 3. Excuse me. Well, if we solve for d, we'll get d equals 3/5. Okay, so I've got one of my values now. Well, unfortunately, there's really not much else to do now other than to multiply things out. So let's multiply things out here and see what we get. So I don't think there's any way I'm going to be able to squeeze this in. So again, you may want to write this down and try multiplying it out and collecting like terms yourself to see if you get the same thing or not. So check my work here. Alright, so this is what I said. Partial fractions is pretty long. There's a lot of little procedures involved here. So let me see if I can't start multiplying it out here. So originally we had an x plus 1 squared. That'll give us x squared plus 2x plus 1. When I multiply out the x squared plus 4 times x plus 1 term, well, that'll give me x cubed plus x squared plus 4x plus 4. And I'm going to go ahead and, you could plug in your d value. I'm going to wait just a second just because I don't want my 3/5 floating around, but I'll do that in a minute. So let me see if I can't squeeze that in here as well. So when I multiply it out, I'll get dx squared plus 4d. Okay, sorry, I'm running out of room here. And again, I have to keep multiplying things out. So I'm going to get an ax cubed. I'll get a 2a x squared, so I'm multiplying out the first stuff, plus ax. Then I'm going to get a bx squared term plus 2bx, I hope I don't make any mistakes, plus b. So that's the first term all being multiplied out. And then, let's see, I'm already running out of room, so let me just squeeze it. So when I distribute the c, I'll get cx cubed plus cx squared plus 4cx plus 4c plus dx squared plus 4d. Yuck. Okay, so a lot of stuff. But again, that's okay. Now let me look. I'm going to start grouping things together. I usually do it in descending order. So I've got an x cubed. I see an x cubed term and an x cubed term. So I'm going to go ahead and start factoring. I'll have a plus c x cubed. That'll take care of the x cubed stuff. Then I start doing my x squared terms. So there's a 2a. That'll take care of that one. There's a plus b. That'll take care of that one. Plus d. That'll take care of the last one. Oh, I left one out. Plus c times x squared. Then I'm going to do my x terms next. So I'm going to put this underneath here. So there's an ax term. There's a 2b x term. There's a plus 4c x term. And that looks like it. And then my b plus 4c plus 4d are all my constant terms. Whew, so pretty tedious. And now this is where the equating of the coefficients comes into it. There's no x cubed term on the left side, so that means that a plus c equals 0. There's no x squared term on the left side, so that means 2a plus b, I'm going to alphabetize it, plus c plus d also equals 0. There's no x term also on the left side, so that means a plus 2b plus 4c equals 0. And lastly, there is a constant term on the left side, so that means b plus 4c plus 4d equals 0. Whew, so yuck. So pretty miserable. Again, a really long problem. Trying to see if I see any magical little shortcuts here that's going to make life tremendously easier, and I don't think there's much that's going to happen here. We could go ahead again and plug in our value that d equals 3/5. We found that from before. So at least that will reduce our system of equations that we have to solve from 4 variables down to, instead of finding the 4 constants, at least now we've got 1 and we'll only have to find 3. So a plus c equals 0. 2a plus b plus c plus 3/5 equals 0. I'm plugging in my d value. A plus 2b plus 4c equals 0. And lastly, b plus 4c plus 4d equals 0. Again, I hope I haven't made a little mistake. It's certainly possible. I'm going through this one pretty quickly. So I certainly apologize if I have. Let's see, what's the best way to do this one here? What I'm going to do is, so let me rewrite this one more time. I'm going to take my first equation and solve that. This will give me that a equals -c. And now I'm going to start plugging that into the other equations. So I'll have, if a is equal to -c, I'll get, plugging that into my second one, I'll get 2 times -c plus b plus c plus 3/5 equals 0. And if I plug it into the third one as well, I'll get -c plus 2b plus 4c equals 0. And I'm not worried about my last one right now. I forgot to plug in my 3/5, but that's okay. Notice now, by doing this, I now have an equation involving c and b. I have 2 equations, 2 unknowns. I can solve this for c and b. If I simplify the first equation, I'll get -2c plus c, which is -c, plus b, plus 3/5 equals 0. On the last one, -c plus 4c, that's 3c plus 2b equals 0. And that'll give me the system of equations -c plus b equals -3/5, rewriting the first one. And then the second one will give me 3c plus 2b equals 0. So I'm going to do elimination by addition and multiply both the first equation by 3. So if I multiply the first equation by 3, I'll get -3c plus 3b equals -9/5 when I multiply the right side by 3. I'll have 3c plus 2b equals 0. And when I add these together, I'll have 5b equals -9/5. If I divide by 5, I'll get that b equals -9/25. So I now have my b value. We already had our d value of 3/5, and usually kind of figuring out the first 1 or 2 is going to be the hard one. Once you have that, it's usually not so bad to go and figure out the other ones. So notice now in my bottom equation I had b plus 4c plus 4d, but I now know what my b value is. I now know what my d value is as well. So b is -9/25 plus 4 times c plus 4 times d, which was 3/5. That equals 0. So this is just a little tedious arithmetic now. So -9/25 plus 4c plus 12/5 equals 0. So this is more just an algebra review at this point more than anything, but just to show you one long example to show you how long it can be and how it's done. If If I get common denominators, I would multiply top and bottom by 5 on my 12/5. So if you multiply, you'll get 60 on top. 60 minus 9, you'll get 51 over 25. Plus 4c equals 0. Well, you could move the negative 51 over 25 over. You would have 4c. You could multiply both sides by 1/4. You would get that c is negative 51 over 100. Last but not least, we had that a was equal to negative c from the very beginning. So if a is equal to negative c, this is going to tell us that a is positive 51 over 100. So we've now got our a value, we've got our b value, we've got our c value, we've got our d value. So it says the original thing that we were trying to integrate in the first place was all of this stuff, and we broke it down as this. So it says our original integral, it says that's going to be ax. So a was 51 over 100 times x, plus b, which is negative 9 over 25. That's all over x squared plus 4, plus c. C again was negative 51 over 100 times x plus 1. And then we figured out our d value to be 3/5. So 3/5 x plus 1 quantity squared. And this is now what we'd be integrating instead, all of this stuff on the top right. Whew. Okay, so pretty long, miserable problem, as you can see. Again, the idea is just using the partial fraction decomposition, and then you know, as you saw, if you're still watching out there, you know, this equating coefficient stuff is going to be pretty nasty because you have to multiply everything out. You end up with a big system of linear equations, and you know, sometimes solving linear equations you have to be a little careful. If you've ever dealt with matrices, you could put it into a matrix and row reduce it, use Gauss-Jordan elimination. Maybe that would be quicker. I don't know that it would be necessarily easy, but again, maybe it would be a little more straightforward. But again, once you have them all, you plug them back in, and you know, again, to integrate this one, we'll talk about actually what you need to do to integrate this stuff in the next video. So I hope this made some sense. Again, I know it's long and miserable. Definitely feel free to try to work it out on your own, compare what I did. Shoot me an email if I made any mistakes, because it's absolutely possible. If you missed the partial fraction decomposition stuff, getting there in the first place, feel free to visit my website. All the videos on doing partial fraction decompositions is there. And last but not least, there'll be another video where actually we do these problems all the way out and finish them off. So good luck. Again, I hope this wasn't too confusing, and I hope I didn't make too many little mistakes.